Hello, all. In today's class, we'll discuss about velocity and acceleration analysis. So, to plot velocity and acceleration diagram, first we should know what is meaning of relative velocity and relative acceleration. So, whenever any link is moving about its orientation or about its fixed point, okay, it has tangential component, that is the velocity component. So, velocity is always tangential to motion that we can plot. And second will be acceleration component. So in acceleration, there are two components. One is normal acceleration, second is tangential acceleration. So in case of component of acceleration, it is always towards the origin, the acceleration component will act, and tangential component will be uh, that is perpendicular to orientation of link. Okay. So normal component of acceleration is given by r omega square, is v square upon r. And tangential component of acceleration is given by r into alpha. Okay. Now we'll discuss one example. So velocity is nothing but rate of change of displacement. Angular velocity is rate of change of angular displacement d theta by dt, and your acceleration will be rate of change of velocity. Now we have again calculations of linear velocity, linear acceleration. So we are using this graphical method. Now to plot this graphical method, again we need to follow some steps. So first we will draw actual configurations diagram as per the given dimensions or given data, we can say. Then we can plot all the velocity components which is tangential to motion. Uh, uh, so velocity, initial velocity of that link we can calculate by taking the speed of that particular link by using equation v is equal to r omega. And after that, intermediate component of that linkages, velocity component of that linkages, we will draw by just connecting a perpendicular lines. Okay. So this is our 4-bar mechanism. So just we'll discuss first how to plot velocity component for this 4-bar mechanism and how to find out relative angular velocity and angular acceleration for this 4-bar mechanisms. Okay. So we have this 4-bar mechanism is given, which is having dimensions of fixed link 180 mm. Then length of intermediate links are given. AB is 90 mm, length of BC is 120 mm, length of CD is given 120 mm. And they have mentioned the speed of crank 100 RPM in clockwise direction. Now, this direction of rotation is also important because as we rotate this link about the orientation, the velocity component will move in the direction of rotation. If it is moving in clockwise direction, so your velocity component will be in right side. If the crank is moving in anti-clockwise direction, the velocity component will be in left side. Okay, that we need to identify. So we will first plot the actual configuration diagram by taking scale 2:1. Okay, so these are the steps. First, we'll mark a line of 180 mm. So 2:1 means just we'll plot line of AD 9 centimeter. Then we'll plot AB link at an angle of 60 degree having dimension 4.5 centimeter because scale is 2:1. This is actually 90 mm. So instead of 90, we can plot 4.5 centimeter. Then next, we will take a second intermediate link BC 6 centimeter, B as a center. By taking B as a center, just draw arc of 6 centimeter. Again, take D as a center, draw second arc of 6 centimeter. So intersection of both these arc will define location of C. So just connect B and C and D. You will get that 4-bar mechanism. So this is our basic configuration diagram of 4-bar mechanism. Okay. After plotting this configuration diagram, we need to draw velocity polygon or velocity diagram. So what we'll do, first we will mark this length. Link of length is available 180 mm, AD fixed length 180, AB 90, BC 120, CD 120. Then we will find out the angular velocity. Angular velocity we need to calculate. Linear velocity we can find out. So crank speed is given 100 RPM. So omega is 2 pi upon 60. So we will get that omega value 10.47 radian per second. And velocity of this point B with respect to A is VAB, or we can say VBA. So VBA is omega into omega B into AB. So omega 10.47, AB value is 90 mm, that is 0.09 meter. So we'll find out this value 0.9425 meter per second. That is the velocity for length AB. Okay. So first we will take that 0.9425 meter per second distance. Now again, to plot that value, the distance should be visible. So we'll take scale 1 centimeter is equal to 0.2 meter per second. So what we'll do, we'll first mark that fixed point with this letter A, comma D, small letter A and D will be, we'll use. for noting that velocity points. So we'll take a perpendicular line to AB having dimensions 4.7 centimeter because scale is 1:0.2. So it is 0.94 upon 0.2 means 4.7 centimeter. So you get velocity component AB. Okay. After this, we have to connect second polygon. So sorry, we have to connect second component, velocity component. How we can connect this second component? We have this perpendicular line for BC, and we have again one more perpendicular component, that is tangential velocity to rotation, that is for CD. So just take this tangential component over to point AD, extend that part, again take this tangential component at B, again extend that part. So these two perpendicular lines will intersect at that point, and that point will represent position of point C. Okay. So simply we will connect that part and we will get point C. So just connect D and C point, B and C point by dark line. So in this way, we will complete this tangential polygon. Okay. After completing tangential polygon, we have to measure these dimensions. So we have to measure this DC distance, CD distance. We have to measure this CB distance. So we have CB distance. Okay. So velocity of component C, velocity of component C with respect to D. This will be your VCD. This will be your VCB. So we have this value 3.15, 3.15. Now, what is our scale? Our scale is 1 centimeter is equal to 0.2 meter per second. So just multiply by scale. So VCB is CB and CB distance into scale 3.15 into 0.2. It is 0.63 meter per second. Similarly, VCD is 3.15 into 0.2, 0.63 meter per second. Okay. These are the velocity component. Okay. Then next, velocity is equal to R into omega. So what is omega? Omega will be velocity upon actual dimensions. That is the length of that particular link. So it is 0.63 upon 0.12 because length is 0.12 for CB. Length of CD is again 0.12. So if you divide by length, then you will get actual angular velocity. So angular velocity of link CB will be 5.25 radian per second. Angular velocity of link CD will be 5.25 radian per second. So in this way, we can plot velocity diagram and we can find out angular velocity. So this is the first part. Now second is acceleration. Okay. Now how to plot acceleration? Now again, we need to find out normal component by taking R into omega square, tangential component by taking R into alpha. Now in our case, we don't have angular acceleration. So angular acceleration will be 0. Okay. So just we'll find out normal acceleration by multiplying R into omega square, R into omega square, R into omega square. So these are the value. Omega for link AB is 10.47, omega for link BC 5.25, omega for link CD 5.25. If you multiply by length and that omega value, omega square value, you will get normal acceleration. So first normal acceleration of AB is 9.87 meter per second square, tangentially 0. For link CB, it is 3.3075 meter per second square. For CD, it is again 3.3075 meter per second square. So normal components are parallel to link that we need to draw, and tangential components are perpendicular to link. So to represent acceleration component, again we'll use small letter A1 D1. Okay. Now first normal component we'll draw parallel line AB1, that is of 9.87 meter per second square. So 1 centimeter is equal to 2 meter per second square. So just we'll draw a line of 4.9 centimeter. That will be a line parallel component to AB. Okay. After this, we have to plot second component, that is a perpendicular component to AB. So just draw perpendicular line for this CB. C is in upward direction, we will plot C in downward direction because velocity is towards the origin. That's why we are plotting this acceleration components towards the origin in opposite direction. So whatever components orientations we have, just we need to replicate same component in opposite direction while plotting acceleration diagram. Okay. So we have A1, B1, we have then B1, Y1. Now this part is around 4.9 centimeter. This part is around 1.67 centimeter. So again, we are plotting only normal component. Again, third normal component we have related to CD. Now C is in upward direction, we'll plot C is in downward direction. So this is the normal component of CD. After plotting normal, we have to draw perpendicular component. So just project one line, perpendicular line, that will represent tangential component of acceleration. So this is tangential component of acceleration for BC. Similarly, we have one more tangential component of acceleration for CD. And these two tangential components will intersect at one point, and that is nothing but your position of point C. So you'll get point C. So just connect that C1 to B1, connect that C1 to D1. So this is your acceleration of C with respect to D, acceleration of C with respect to B, A, B, C, and ACD. Okay. Now, what is our what is defined in our problem statement? We need to determine angular acceleration. Okay, that is angular accelerations we have to find out. So to get that angular acceleration, first we should know the value of tangential acceleration. So we have tangential acceleration c1y1 for link BC, 2.45 centimeter, that is the distance, multiplied by scale 2. So this value is 4.9 meter per second square. Similarly, we have one more tangential acceleration c1x1, that is 5.15 centimeter, multiplied by scale 2. So it is around 10.3 meter per second square. So in this way, we can calculate tangential acceleration for CD, tangential acceleration for BC. And angular acceleration of that link will be tangential acceleration AT is equal to R into alpha, that is acceleration upon BC. So we'll get acceleration value 40.83 radian per second square, 85.83 radian per second square. Okay. So in this way, we can find out the acceleration value.